So here's something that might catch you off guard. Right now, as you're lying there, settling in, getting comfortable, there are materials in the world, real, physical materials you could hold in your hand, that can carry electricity forever. Not for a long time. Not for a really, really long time. Forever. No loss, no resistance, no heat. You send a current flowing through them and it just keeps going. Around and around, like a train on a circular track with no friction, no air resistance, nothing to slow it down. Scientists have set up experiments where they started a current flowing in a superconducting ring and then watched it, and waited, and checked back, and the current was still flowing, unchanged, years later. Not diminished by some tiny fraction, unchanged. As far as anyone can tell, it would keep going until the end of the universe, as long as you keep the material cold enough. That's superconductivity. And I know, it sounds like science fiction. It sounds like one of those things someone tells you at a party and you nod politely but quietly assume they're exaggerating. But they're not. This is real. This is verified. This is one of the strangest, most beautiful, most stubbornly mysterious phenomena in all of physics. And tonight, we're going to walk through the whole story. How it was discovered, why it happens, what makes it so confusing, and why, more than a century after someone first stumbled onto it, we're still trying to fully understand it. But let's start at the beginning. And the beginning isn't really about superconductors at all. It's about cold. Think about temperature for a second. You know what temperature is, intuitively. It's how hot or cold something feels. But at a deeper level, temperature is really about motion. The atoms and molecules in any material are constantly jiggling, vibrating, bouncing around. The hotter something is, the more frantic that motion becomes. The colder it gets, the more those atoms settle down, calm down, move less. And if you could cool something all the way down to absolute zero, minus 273.15 degrees Celsius, or 0 Kelvin, theoretically, that motion would stop entirely. The atoms would be as still as the laws of quantum mechanics allow, which, it turns out, isn't perfectly still, but that's a wrinkle we'll get to much later. Now, for most of human history, we couldn't get anywhere close to those temperatures. Cold was whatever winter gave you. But in the 1800s, physicists and chemists started figuring out how to liquefy gases, how to take things that are normally invisible and flowing, like oxygen and nitrogen, and cool them down so much that they become liquids. And this became a race, a genuine, competitive, ego-driven race among some of the best scientific minds in Europe. The key figure in our story is a Dutch physicist named Heike Kamerlingh-Onnes, and I want you to get a picture of this guy because he's important. Born in 1853 in Groningen, the Netherlands, Kamerlingh-Onnes was meticulous, obsessively so. He ran his laboratory at the University of Leiden like a precision instrument. He trained his own glassblowers and technicians. He built custom equipment. His motto, which he had inscribed on the wall of his lab, was "Door meten tot weten," through measurement to knowledge. He wasn't interested in grand theories or philosophical speculation. He wanted to measure things. He wanted to push into temperature regimes no one had ever reached and see what happened. And the great prize, the white whale of low-temperature physics at the turn of the 20th century, was helium. Every other known gas had been liquefied by then. Oxygen, nitrogen, hydrogen, one by one they'd been conquered. But helium held out. Helium has the lowest boiling point of any element. To liquefy it, you need to get down to about 4.2 Kelvin. That's 4.2 degrees above absolute zero. Staggeringly, almost incomprehensibly cold. On July 10th, 1908, Kamerlingh-Onnes and his team did it. After years of preparation, after building an elaborate cascade of cooling stages, using liquid air to cool hydrogen and liquid hydrogen to cool helium in a series of carefully designed steps, they managed to liquefy helium for the first time. It was a triumph. It made headlines. And it gave Kamerlingh Onnes something no other scientist on Earth had: a way to study materials at temperatures just a few degrees above absolute zero. So what do you do when you have the coldest laboratory in the world? You start testing things. You start asking, what happens to the properties of materials when you make them this cold? And one of the most natural questions to ask was about electrical resistance. Here's the thing about electrical resistance. You already know intuitively what it is. When you run electricity through a wire, the wire gets warm. That's resistance. The electrons flowing through the metal are bumping into things, into the vibrating atoms of the metal lattice, into impurities, into defects in the crystal structure. Each collision costs a little energy, and that energy shows up as heat. That's why your phone charger gets warm. That's why the filament in an old incandescent light bulb glows. The resistance is so high that the wire gets white hot. Now, physicists in the early 1900s knew that resistance generally decreases as you cool a metal down. Makes sense, right? The atoms vibrate less when they're colder, so there's less for the electrons to bump into. The question was, what happens when you go really, really cold? What happens as you approach absolute zero? There were three competing theories at the time. Some scientists thought the resistance would just keep dropping smoothly and reach zero right at absolute zero, a nice, clean, satisfying curve down to nothing. Others, including Lord Kelvin himself, thought that at very low temperatures, the electrons would actually freeze in place and stop moving, so the resistance would shoot back up. And a third camp thought the resistance would flatten out at some small but non-zero value, because there would always be impurities and defects for the electrons to scatter off of, no matter how cold you made the metal. Kamerlingh Onnes decided to settle the question experimentally. He chose mercury as his test material, partly because it could be highly purified through distillation. You could get very clean samples, which reduced the complication of impurities. And in 1911, he and his team started cooling a thin capillary tube of mercury down toward absolute zero, carefully measuring its electrical resistance at each step. What they found was, by any measure, one of the most shocking results in the history of physics. As they cooled the mercury, the resistance dropped, just as expected. Smoothly, gradually, predictably. And then, at about 4.2 Kelvin, right around the boiling point of liquid helium, the resistance didn't just decrease. It didn't taper off. It fell off a cliff. It dropped to zero. Not approximately zero. Not very small. Zero. As far as their instruments could measure, the electrical resistance of mercury had simply vanished. Kamerlingh Onnes was a careful man. He didn't trust it at first. He and his team repeated the measurement. They checked their instruments. They tried different samples. The result held. Below a certain critical temperature, mercury had no electrical resistance whatsoever. Current could flow through it without any loss at all. He called it supraconductivity initially. The word evolved into superconductivity over time, and he published his results in 1911, noting, with characteristic understatement, that mercury had passed into a new state, which on account of its extraordinary electrical properties may be called the superconductive state. Think about what that means for a second. In our everyday experience, every wire, every circuit, every electrical device wastes energy to resistance. Your power grid loses something like 5 to 10% of all the electricity it transmits just to resistance in the wires. That energy doesn't go anywhere useful. It just heats up the cables. If you could make wires out of superconductors, that loss would be zero. Zero. The implications were staggering, and Kamerlingh-Onnes knew it immediately. He started dreaming about superconducting electromagnets that could create enormous magnetic fields without consuming any power. He envisioned a revolution in electrical engineering. But there was a catch. There's always a catch. And Kamerlingh-Onnes discovered it pretty quickly. When he tried to run large currents through his superconducting mercury, the kind of currents you'd need to make a powerful electromagnet, the superconductivity broke down. Above a certain current, the material snapped back to being a normal, resistive metal. And the same thing happened with magnetic fields. Apply too strong a magnetic field, and the superconductivity was destroyed. There was a critical temperature, a critical current, and a critical magnetic field, and if you exceeded any of them, the magic went away. This was disappointing. It meant you couldn't just wind a superconducting coil and crank up the current to get an incredibly powerful magnet. The superconductor wouldn't let you. It had limits, and those limits were frustratingly low. Still, the discovery was enormous. Kamerlingh-Onnes won the Nobel Prize in Physics in 1913, primarily for his work on liquefying helium and the investigations it enabled, including the discovery of superconductivity. And his laboratory in Leiden became the world capital of low-temperature physics, a place where researchers from across Europe came to study the strange new phenomena that emerged at the edge of absolute zero. But here's what's fascinating, and this is something that doesn't get talked about enough. For decades after the discovery, nobody had any idea why superconductivity happened. None. They could describe it. They could measure it. They could catalog which materials did it and at what temperatures. But the mechanism, the actual reason that resistance vanished, remained a complete mystery. And it wasn't for lack of trying. Some of the greatest minds of the 20th century took a crack at it. Albert Einstein proposed a theory in 1922 that turned out to be wrong. Niels Bohr thought about it. Werner Heisenberg thought about it. Felix Bloch, one of the founders of solid-state physics, reportedly proved a theorem that superconductivity was impossible, which was, of course, embarrassing since it clearly existed. The joke in physics circles was that every theory of superconductivity could be disproved. Bloch's theorem wasn't really a formal theorem, more of a running frustration expressed as dark humor, but it captured the mood. The problem was hard. Really, genuinely, stubbornly hard. Part of what made it so difficult was that superconductivity is fundamentally a quantum mechanical phenomenon. It arises from the collective quantum behavior of enormous numbers of electrons. And in the early decades of the 20th century, quantum mechanics itself was still being invented. The tools needed to understand superconductivity literally didn't exist yet. It's like trying to solve a jigsaw puzzle when half the pieces haven't been manufactured. So for a long time, the experimental side raced ahead, while the theoretical side struggled to keep up. Researchers kept finding new superconductors: tin, lead, niobium, various alloys. They mapped out the critical temperatures, the critical fields, the critical currents. They noticed patterns. They found that good conductors like copper and gold and silver, the metals you'd most expect to be superconductors, stubbornly refused to superconduct. Meanwhile, relatively poor conductors like lead and mercury were the ones that made the transition. That was puzzling. That was a clue, though nobody quite knew what to do with it yet. And then, in 1933, something happened that made the mystery even deeper. Two German physicists, Walter Meissner and Robert Oxenfeld, discovered something about superconductors that nobody had predicted, and that, honestly, nobody was quite prepared for. They found that when you cool a superconductor below its critical temperature in the presence of a magnetic field, the superconductor doesn't just allow the field to pass through it. It actively expels the magnetic field from its interior, pushes it out completely. The magnetic field inside a superconductor is zero, not because the field was never there, but because the superconductor generates its own currents on its surface that create an opposing field, perfectly canceling the external one inside the material. This is called the Meissner effect, and it's the reason you've probably seen those dramatic demonstrations where a small magnet hovers, levitating, above a superconductor. The superconductor is pushing the magnetic field away so aggressively that it physically repels the magnet. It floats there, stable, motionless, like a magic trick. But it's not magic. It's the Meissner effect. And here's why this was such a big deal, theoretically. Before Meissner and Oxenfeld's discovery, you might have been tempted to think of a superconductor as simply a perfect conductor, a material with zero resistance, nothing more. And a perfect conductor would indeed have some interesting magnetic properties. If you tried to change the magnetic field inside a perfect conductor, the zero resistance would allow currents to flow that would oppose the change, keeping the field constant. But, and this is the crucial distinction, a perfect conductor would trap whatever magnetic field was already inside it when it became perfectly conducting. It would freeze the field in place. A superconductor doesn't do that. A superconductor expels the field. Even if the field was there before the material became superconducting, once it crosses below that critical temperature, the field gets pushed out. That means superconductivity isn't just perfect conductivity. It's something more, something different, something that involves a fundamentally new state of matter, a thermodynamic phase, like the difference between water and ice. The transition to superconductivity is a phase transition, and the Meissner effect is the proof. This distinction might seem subtle, but it's actually enormous. It told physicists that any successful theory of superconductivity would have to explain not just zero resistance, but also this active expulsion of magnetic fields. It raised the bar considerably, and it meant that the theoretical puzzle was even harder than everyone had thought. So by the mid-1930s, the situation was this. Superconductivity had been known for over 20 years. A growing list of materials had been found to exhibit it. The Meissner effect had added a whole new layer of mystery. And still, no one could explain why any of it happened. The greatest theoretical physicists of the age had tried and failed. The answer, when it finally came, would take another 2 decades, and it would come from a rather unlikely trio of physicists working in Urbana, Illinois, at the University of Illinois. Their names were John Bardeen, Leon Cooper, and John Robert Schrieffer, and the theory they built together, known forever after by their initials, BCS, would finally crack the puzzle that had defeated some of the greatest minds of the 20th century. But to understand how they got there, you really need to know a little about who these three were, because the story of BCS theory is as much a human story as it is a physics story. Let's start with John Bardeen, because he's one of the most quietly remarkable figures in the entire history of science. Bardeen was born in 1908 in Madison, Wisconsin. His father was the dean of the medical school at the University of Wisconsin, so he grew up in an academic household, but he wasn't some flashy prodigy who made headlines. He was just deeply, relentlessly smart, in a way that was easy to underestimate because he was also deeply, relentlessly quiet. Colleagues would later describe him as the most understated genius they'd ever met. He'd sit in a meeting, saying almost nothing, and then at the very end, he'd make one comment that cut right to the heart of the problem. He had this extraordinary ability to listen, to absorb, to think slowly and carefully, while everyone around him was rushing to be clever. Here's the thing about Bardeen that makes his story almost absurd. By the time he turned his attention seriously to superconductivity in the early 1950s, he had already co-invented the transistor. Think about that. The transistor, the device that made modern electronics possible, that's in every computer, every phone, every piece of digital technology you've ever touched. Bardeen, along with Walter Brattain and William Shockley at Bell Labs, had created it in 1947, and he'd shared the Nobel Prize in Physics for it in 1956. Most people would consider that a career. Most people would coast on that for the rest of their lives. Bardeen decided he wanted to solve superconductivity, and there's actually a painful backstory to why he left Bell Labs and ended up in Illinois. The transistor team at Bell Labs had been led officially by William Shockley, who was brilliant, but also, to put it gently, extraordinarily difficult to work with. Shockley was competitive, paranoid about credit, and increasingly erratic. After the transistor breakthrough, the working relationship between Bardeen and Shockley deteriorated badly. Shockley essentially pushed Bardeen out of semiconductor research at Bell Labs, claiming the territory as his own. So Bardeen left. He went to the University of Illinois at Urbana-Champaign in 1951, and he decided to tackle the biggest unsolved problem in condensed matter physics. It was, in a way, a response to being pushed aside, a quiet, determined response from a quiet, determined man. Now, the second member of the trio. Leon Cooper was a young theoretical physicist from New York, Columbia-educated, sharp and fast, where Bardeen was slow and careful. Cooper had been trained in quantum field theory, which was the hot topic in theoretical physics at the time, the physics of fundamental particles and forces. He didn't know much about solid-state physics when he arrived at Illinois in 1955 as a postdoc. But Bardeen had specifically recruited him because he wanted someone with that quantum field theory toolkit, someone who could think about the problem from a completely different angle. And this turned out to be a stroke of genius, because Cooper brought a fresh perspective that the solid-state community had been missing. The third member was Robert Schrieffer, and he was the youngest, a graduate student, just 25 years old when the theory came together. Schrieffer was Bardeen's PhD student, and he was the one who would ultimately write down the mathematical form of the theory's ground state, the wave function that described what all the electrons in a superconductor were actually doing. It's a remarkable thing, when you think about it, that one of the most important theoretical breakthroughs in 20th century physics was partly the work of a graduate student. But that's how it happened. So what did they figure out? Let's walk through it, slowly, because this is one of those ideas that seems impossible at first, but becomes beautiful once you see it. The fundamental question was this: why do electrons in a superconductor behave so differently from electrons in a normal metal? In a normal metal, electrons carry current, but they're constantly bumping into things, into the vibrating atoms of the metal lattice, into impurities, into defects. Every collision costs them a little energy, and that energy loss is what we call electrical resistance. It's why wires get warm when current flows through them. The energy of the moving electrons gets converted into heat, into random atomic vibrations. That's resistance. That's the thing that superconductors somehow eliminate entirely. Now, here's the deep problem. Electrons are fermions. If you remember a little quantum mechanics, or even if you don't, just take this on faith for a moment. Fermions are particles that refuse to share the same quantum state. This is the Pauli exclusion principle, and it's one of the most fundamental rules in physics. It's why the periodic table looks the way it does, why atoms have shells of electrons, why matter has structure at all. Electrons, being fermions, are loners. They each insist on having their own unique quantum state, and this makes it very hard to get them to do anything collectively, anything coordinated. In a normal metal, electrons behave more or less independently, each one doing its own thing, each one scattering off atoms on its own schedule. But superconductivity is clearly a collective phenomenon. The current flows without any resistance, which means the electrons must somehow be moving in perfect coordination in a way that prevents any individual electron from scattering and losing energy. How do you get a bunch of loner particles to suddenly cooperate like that? This is where Leon Cooper's contribution comes in, and it's genuinely one of the most surprising results in all of physics. In 1956, Cooper showed that if you have a metal at very low temperatures, and you consider just 2 electrons near the Fermi surface, that's the energy level where the highest energy electrons in the metal sit. Those 2 electrons can form a bound pair, even though they're both negatively charged and should repel each other. Let that sink in for a second. 2 electrons, both negative, both pushing each other away with the electromagnetic force, and yet they can bind together into a pair. How? The answer is phonons. And phonons are one of those concepts that sounds intimidating, but is actually pretty intuitive once you think about it. A phonon is just a quantum of vibration in the crystal lattice, a little packet of sound, essentially. When an electron moves through a metal lattice, it tugs on the positively charged atoms around it, because the electron is negative and the atomic nuclei are positive. The electron pulls the nearby atom slightly toward it as it passes, creating a tiny, temporary region of extra positive charge. And that region of positive charge can attract another electron. So the first electron distorts the lattice distortion attracts the second electron, and the net effect is that the 2 electrons are attracted to each other, indirectly, through the lattice. The lattice is acting as a matchmaker, you might say. Now, this attraction is incredibly weak, ridiculously weak. It's overwhelmed by the direct electrical repulsion between the electrons at normal temperatures. But at very low temperatures, when thermal vibrations die down and everything gets quiet, this tiny phonon-mediated attraction can win out. The 2 electrons form what we now call a Cooper pair. And here's the really wild part. The 2 electrons in a Cooper pair are not sitting right next to each other. They're not huddled together like 2 people sharing a blanket. They can be hundreds of nanometers apart, which in atomic terms is enormous. Thousands of other atoms sit between them. It's more like 2 dancers on opposite sides of a ballroom who are somehow perfectly synchronized despite the crowd between them. And here's where the magic happens. A Cooper pair, made of 2 fermions, is itself a boson. This is crucial. Bosons are the opposite of fermions in one key respect. They love to share quantum states. Photons are bosons, which is why you can get trillions of photons all doing the exact same thing in a laser beam. So when electrons pair up into Cooper pairs, they transform from antisocial fermions into gregarious bosons, and all the Cooper pairs can collapse into the same quantum state, the same energy, the same momentum, the same everything. They form what physicists call a condensate, a single macroscopic quantum state where all the pairs are moving in lockstep. And when all the pairs are in the same state, something extraordinary happens to scattering. Remember, resistance comes from electrons scattering off lattice vibrations and impurities. But to scatter a Cooper pair, you'd have to break it apart, and breaking a Cooper pair costs energy. There's a gap, an energy gap, between the paired state and the unpaired state. At low enough temperatures, there simply isn't enough thermal energy available to break the pairs, so scattering can't happen. Current flows and nothing can stop it. The resistance drops to zero. Not approximately zero, not very small, exactly zero. This is BCS theory, and when Bardeen, Cooper, and Schrieffer published it in 1957, it was immediately recognized as a triumph. It explained zero resistance. It explained the Meissner effect, because the energy gap and the coherent quantum state of the condensate make it energetically favorable for the superconductor to generate screening currents that push out magnetic fields. It explained the critical temperature, the critical field, the critical current, all those thresholds that Ons had discovered decades earlier. It explained why some materials superconduct and others don't, based on the strength of the electron-phonon coupling. It was comprehensive, elegant, and correct. Bardeen won his second Nobel Prize for it in 1972, shared with Cooper and Schrieffer. Think about that. 2 Nobel Prizes in physics, one for the transistor and one for BCS theory. He remains the only person ever to have won 2 Nobel Prizes in the same field, and he was still the same quiet, unassuming guy. There's a famous story that when he went to Stockholm for the first Nobel ceremony in 1956, the King of Sweden gently scolded him for not bringing his children. So in 1972, he made sure to bring them. Now, BCS theory was beautiful, and it worked wonderfully for the superconductors that were known at the time, metals like mercury, lead, tin, niobium, and various alloys. These are what we now call conventional superconductors, or type 1 superconductors, and they all share certain characteristics. They're all metals or metallic alloys. They all have very low critical temperatures. The highest was niobium germanium at about 23 Kelvin, discovered in 1973, and that seemed like it might be close to the ceiling. And they all work through the phonon mechanism that Cooper had identified, lattice vibrations mediating the attraction between electrons. But even as BCS theory was being celebrated, there were hints that the story wasn't complete. Because alongside the clean, well-behaved type 1 superconductors, there was another class of materials that behaved differently in magnetic fields. Materials where the Meissner effect wasn't total, where magnetic field lines could partially penetrate the material in the form of tiny quantized vortices, little tubes of magnetic flux threading through an otherwise superconducting bulk. These were called Type 2 superconductors, and a Soviet physicist named Alexei Abrikosov had predicted their behavior theoretically in 1957, building on earlier work by Vitaly Ginzburg and Lev Landau. The Ginzburg-Landau theory, which predated BCS by a few years, was a phenomenological theory, meaning it described the behavior of superconductors mathematically without explaining the microscopic mechanism. It used an order parameter, a kind of mathematical field that described the degree of superconducting order at each point in the material, and it was remarkably powerful for predicting how superconductors would behave near their critical temperature, near surfaces, and in magnetic fields. What Abrikosov showed was that in certain materials, the boundary between the superconducting and normal states has a negative surface energy, which means it's energetically favorable for the material to create as much boundary as possible. And the way it does that is by letting magnetic flux penetrate in the form of many thin vortices, each carrying exactly 1 quantum of magnetic flux. These vortices arrange themselves in a regular lattice, an Abrikosov vortex lattice, and the material remains superconducting everywhere, except in the tiny cores of the vortices. This means type 2 superconductors can tolerate much higher magnetic fields than type 1 materials because they don't have to expel the field entirely. They just let it through in controlled, quantized doses. And this distinction turns out to be enormously important for practical applications because almost every superconductor that's actually useful in technology is type 2. The magnets in MRI machines, the magnets in particle accelerators, like the Large Hadron Collider at CERN, the superconducting cables in experimental fusion reactors. They're all made from type 2 superconductors, materials like niobium titanium and niobium tin, because only type 2 materials can carry large currents in strong magnetic fields without losing their superconductivity. Type 1 materials are scientifically fascinating, but practically limited because their critical fields are just too low. So by the early 1970s, the theoretical picture seemed fairly complete. BCS theory explained the microscopic mechanism. Ginzburg-Landau theory described the macroscopic behavior. Abrikosov had explained type 2 superconductors, and the whole framework hung together beautifully. The critical temperatures were low, always below about 23 Kelvin, always requiring expensive liquid helium for cooling. And many physicists believed that was simply a fundamental limitation. There were theoretical arguments suggesting that phonon-mediated superconductivity had a natural ceiling, that you couldn't push the critical temperature much higher because the same lattice vibrations that created Cooper pairs would, if they got too strong, simply destroy the crystal structure instead. The field settled into a kind of comfortable maturity. The big questions had been answered. The applications were being developed. And then, in 1986, something happened that nobody saw coming. Two researchers at an IBM laboratory in Rüschlikon, Switzerland, a small town just outside Zurich, published a paper that would turn the entire field upside down. Their names were Georg Bednorz and Alex Müller, and what they found was so unexpected, so contrary to everything the community believed, that at first, almost nobody took it seriously. Let's talk about who these two were, because their story matters. Alex Müller was the senior figure, a Swiss physicist in his late 50s who had spent most of his career studying oxides, ceramic materials, the kind of stuff you might associate with pottery or bathroom tiles more than with cutting-edge physics. He had a deep intuition about these materials, a feeling that had been building for years that oxides were hiding something interesting. Müller wasn't a superconductivity specialist. He came from a different corner of condensed matter physics, and maybe that's exactly why he could see what the specialists couldn't. Sometimes the most important breakthroughs come from outsiders, people who aren't so deeply embedded in the conventional wisdom that they can't imagine alternatives. Georg Bednorz was younger, a German physicist in his mid-30s, and he had been Müller's doctoral student before becoming his research partner at IBM. The two of them had been quietly working on oxide materials for a couple of years, testing different compositions, looking for signs of superconductivity in compounds that no serious superconductivity researcher would have bothered with. Because here's the thing. The established wisdom said that superconductors were metals and metallic alloys. That's where you looked. Ceramics were insulators, or at best, mediocre conductors. The idea that a ceramic oxide could superconduct seemed almost absurd. But Müller had a hunch. He had been reading about certain oxide compounds that showed unusual electrical properties, and he had a theoretical intuition, partly based on a concept called John Teller polarons, that certain copper oxide structures might support a kind of strong electron lattice coupling that could lead to superconductivity at higher temperatures than anyone expected. It wasn't a fully worked out theory. It was more like a scent on the wind, a feeling that something was there if you looked in the right place. So they started testing barium lanthanum copper oxide compounds, mixing powders, pressing pellets, firing them in furnaces, cooling them down, and measuring their resistance. It was painstaking work, and for a long time, nothing remarkable happened. But in January of 1986, Bednorz measured a sample, a specific composition of lanthanum, barium, copper, and oxygen, and saw the resistance begin to drop sharply at around 35 Kelvin. 35 Kelvin. Remember, the previous record for a superconducting critical temperature had been 23 Kelvin, set by a niobium-germanium alloy back in 1973. And here was a ceramic, a brittle oxide that you could crumble between your fingers, showing signs of superconductivity at a temperature more than 50% higher than the old record. They were cautious. They had to be. The measurement was noisy, the transition wasn't perfectly clean, and they knew how extraordinary the claim was. Bednorz and Müller spent months refining their samples, repeating the measurements, trying to rule out artifacts. When they finally published their results in September 1986, they did it in a German physics journal, Zeitschrift für Physik B, and they used deliberately cautious language. The title of the paper mentioned possible high-temperature superconductivity. With that careful word, possible, doing a lot of heavy lifting, they were essentially saying, "We think we found something incredible, but we're not going to oversell it." And at first, the reaction was mostly silence. A few groups noticed the paper, but many physicists were skeptical. Ceramics? Superconducting at 35 Kelvin? It didn't fit the paradigm. Some people assumed there must be an error, some metallic impurity in the sample that was responsible for the signal. Others simply didn't pay attention. The paper was published in a journal that wasn't widely read by the American physics community. But then a few groups started trying to reproduce the results. And here's where the story accelerates in a way that's almost unprecedented in the history of physics. By late 1986, a group in Tokyo led by Shoji Tanaka confirmed the result. Then Paul Chu at the University of Houston got interested, and Chu was exactly the kind of relentless, competitive experimentalist who could push things further. Chu started systematically varying the composition, substituting different elements, applying pressure, trying to push the critical temperature higher. And in January of 1987, Chu and his collaborator, Ma Kuen-Wu at the University of Alabama in Huntsville, made a discovery that sent shockwaves through the entire physics community. They found that a compound of yttrium, barium, copper, and oxygen, which would come to be known as YbCO, or sometimes just 1,2,3 because of its chemical formula, Yba2Cu3O7, became superconducting at about 93 Kelvin. 93 Kelvin. Let that sink in for a moment. The previous record had been 23 Kelvin, and Bednorz and Müller had pushed it to 35. Now Chu and Wu had blown past it to 93. But the number itself isn't even the most important part. What matters is what 93 Kelvin means practically, because liquid nitrogen boils at 77 Kelvin, and liquid nitrogen is cheap, incredibly cheap. You can buy it for less than the price of milk. It's used industrially all over the world. Liquid helium, which you need to cool conventional superconductors, is expensive, scarce, requires specialized equipment, and boils away constantly. Liquid nitrogen is something you can pour out of a thermos. So a superconductor that works at 93 Kelvin is a superconductor you can cool with liquid nitrogen. And that changes the economics of superconductivity completely. It was as if someone had discovered a way to make gold out of dirt. The practical implications seemed limitless. What followed was one of the most extraordinary periods in modern physics. It became known as the Woodstock of Physics, a legendary session at the American Physical Society meeting in New York City on March 18, 1987. The session was scheduled for the evening in a ballroom at the Hilton, and it was supposed to be a regular contributed paper session, but word had gotten out about the new superconductors, and by the time the doors opened, thousands of physicists were trying to get in. The room held about 1,100 people, and the overflow crowd watched on television monitors in the hallway. The session started at 7:30 in the evening and didn't end until 3:15 in the morning. Speaker after speaker presented new results, new materials, higher critical temperatures, new measurements confirming the phenomenon. People were standing on chairs. The excitement was almost delirious. Paul Chu presented his YBCO results. Miller spoke. Dozens of groups from around the world shared their findings. It was the kind of night that physicists who were there still talk about decades later, the kind of night where you could feel the ground shifting under an entire field. And the frenzy wasn't confined to that one meeting. In labs around the world, the race was on. Groups in China, Japan, the United States, Europe, everyone was mixing copper oxide ceramics, trying new compositions, hunting for even higher critical temperatures. Within months, new families of high-temperature superconductors were discovered. Bismuth, strontium, calcium, copper oxide compounds pushed the critical temperature above 100 Kelvin. Thallium-based cuprates went higher still, reaching about 125 Kelvin. Eventually, mercury, barium, calcium, copper oxide compounds would reach about 133 Kelvin at ambient pressure, and even higher under extreme pressure. Each new record was announced with breathless excitement. Bednorz and Müller won the Nobel Prize in Physics in 1987, just 1 year after their original publication. That's almost unheard of. The Nobel Committee usually waits years or decades to make sure a discovery holds up. The speed of the award tells you how significant the committee considered the discovery. And it was significant, not just because of the higher temperatures, but because these materials were fundamentally different from anything BCS theory was designed to explain. And this is where things get really interesting from a physics perspective, and also a little humbling. Because remember how beautifully BCS theory explained conventional superconductors? Cooper pairs formed through phonon-mediated interactions, condensing into a coherent quantum state with an energy gap? Well, the cuprate high-temperature superconductors clearly involved Cooper pairs. The electrons were definitely pairing up. You could measure that. But the mechanism holding them together didn't seem to be phonons, or at least not primarily phonons. The isotope effect, which had been one of the key pieces of evidence for phonon-mediated pairing in conventional superconductors, was weak or absent in the cuprates. The crystal structures were completely different. Layered perovskite structures with copper oxygen planes that seemed to be where the superconductivity lived. The normal state properties were strange too. Above their critical temperatures, these materials didn't behave like normal metals. They had unusual resistivity curves, peculiar magnetic properties, a mysterious pseudo-gap that appeared at temperatures well above the superconducting transition. Think about what that means for the field. You had this beautiful, complete theory, BCS, that explained everything about conventional superconductors, and now you had a whole new class of materials that were clearly superconducting, clearly forming Cooper pairs, but doing it through some mechanism that BCS couldn't account for. It was as if you'd spent decades understanding how gasoline engines work, and then someone handed you a car that ran perfectly but had no engine under the hood. The car clearly worked. You just couldn't explain how. And here we are, decades later, and the honest truth is that we still don't have a complete, universally accepted theory of high-temperature superconductivity in the cuprates. There are leading candidates. Many physicists believe that magnetic interactions play a crucial role, specifically that the copper-oxygen planes in these materials have strong anti-ferromagnetic correlations, and that these magnetic fluctuations can mediate pairing between electrons in a way that's analogous to, but fundamentally different from phonon-mediated pairing. The symmetry of the pairing is different too. In conventional superconductors, the Cooper pairs have what's called S-wave symmetry. The energy gap is roughly the same in all directions. In the cuprates, the pairing has D-wave symmetry, meaning the gap has nodes, directions where it goes to zero. This was confirmed through a series of elegant experiments in the 1990s, and it was a major clue about the pairing mechanism, because D-wave symmetry is exactly what you'd expect from magnetic pairing, but not from simple phonon pairing. But even knowing the symmetry, even having strong circumstantial evidence pointing toward magnetic interactions, the full theory remains elusive. The problem is that these materials are what physicists call strongly correlated electron systems, meaning the electrons interact with each other so powerfully that you can't treat them as nearly independent particles the way you can in ordinary metals. The mathematical tools that work so well for conventional superconductors, perturbation theory, mean field approaches, break down when correlations are this strong. You're dealing with a quantum many-body problem of extraordinary complexity, the kind of problem that even the most powerful computers struggle with. And that unsolved puzzle sits at the heart of one of the biggest questions in condensed matter physics. If we truly understood the mechanism behind high-temperature superconductivity, could we design materials with even higher critical temperatures? Could we find a room-temperature superconductor? The cuprates showed us that the old ceiling of 23 Kelvin was not fundamental at all. It was just the limit of one particular mechanism. Nature clearly has other tricks. The question is whether those tricks can take us all the way to room temperature. And to answer that, you'd really want to understand what those tricks are. Now, while theorists were wrestling with the cuprate puzzle, experimentalists were discovering that the cuprates themselves had some serious practical challenges. Because here's the thing about these materials that gets overlooked in all the excitement about high critical temperatures. They're ceramics. They're brittle. You can't draw them into wires the way you can with niobium titanium. If you try to bend them, they crack. And superconducting applications almost always need wires or cables, long flexible conductors that can be wound into coils for magnets or strung along power lines for transmission. So the materials science challenge was enormous. How do you take a brittle ceramic and turn it into something that behaves like a wire? The answer that emerged involved some genuinely clever engineering. One approach, developed over years of painstaking work, was the powder-in-tube method. You take the superconducting ceramic in powder form, pack it into a silver tube. Silver because it's compatible with the ceramic and doesn't react with it at high temperatures. And then you draw the tube down into a thin wire through a series of mechanical steps, heating and rolling and drawing, over and over. The result is a composite wire with thin filaments of superconducting ceramic embedded in a silver matrix. It works, but it's expensive, and the current carrying capacity, while useful, isn't as high as you'd want for many applications. Later, thin film techniques were developed for what are called coated conductors, or second-generation high-temperature superconducting wire, where a thin layer of YBCO is deposited on a flexible metal tape with carefully engineered buffer layers to align the crystal structure. Getting the crystal grains aligned turns out to be critical, because in these cuprate materials, current flows easily along the copper-oxygen planes, but very poorly perpendicular to them. And if the grains in your wire are randomly oriented, the current has to cross grain boundaries where the crystal directions don't match, and that kills the performance. So there was this whole parallel engineering effort, materials scientists and engineers working for years to figure out how to make these miraculous but uncooperative materials into something you could actually build things with. And meanwhile, the theorists were still arguing about the mechanism, and the experimentalists were still hunting for new superconductors, and the whole field had this wonderful, slightly chaotic energy to it, because the discovery of the cup rates had broken open the assumption that we understood the limits of superconductivity, and once that assumption was gone, people started looking everywhere. What other materials might superconduct at high temperatures? What other mechanisms might be out there, waiting to be found? And one of the most surprising places they looked was right back at the periodic table's simplest building blocks: iron. Of all things, iron. Now, if you'd told a superconductivity researcher in, say, 2005 that iron-based compounds would become the next big family of superconductors, they probably would have laughed, and not a polite laugh either, because iron is magnetic. It's one of the three elements, iron, cobalt, nickel, that are ferromagnetic at room temperature. And magnetism, as we talked about way back when we were thinking about the Meissner effect, is basically the enemy of superconductivity. Superconductors expel magnetic fields. Ferromagnets generate them. The two phenomena seem fundamentally opposed, like trying to mix oil and water. So the idea that you could build a superconductor out of iron felt almost absurd. It would be like saying, hey, let's make a fireproof material out of kindling. But nature, as it turns out, doesn't care about our intuitions. In February 2008, a Japanese physicist named Hideo Hosono at the Tokyo Institute of Technology published a paper announcing that he had found superconductivity in an iron-based compound, specifically a layered material made of lanthanum, oxygen, iron, and arsenic, with some of the oxygen atoms replaced by fluorine. The chemical formula was LeOphias with fluorine doping, and it superconducted at about 26 Kelvin. Now 26 Kelvin doesn't sound like much compared to the cuprates, right? YBCO was up at 93 Kelvin, and the mercury-based cuprates had reached 133. But the significance wasn't the temperature. The significance was the iron. Here's the thing. Hosono's discovery wasn't entirely out of nowhere. He had been working on layered oxypnictides for years, studying their electrical and optical properties. Pnictides, by the way. That's just the name for the group of elements that includes nitrogen, phosphorus, arsenic, antimony, and bismuth. The nitrogen family on the periodic table. So these materials had layers of iron and arsenic sandwiched between layers of lanthanum and oxygen, and Hosono had been methodically exploring their behavior. He wasn't specifically hunting for superconductivity, at least not at first. He was interested in these materials as potential transparent conductors and semiconductors. But as he doped them, swapping in fluorine for some of the oxygen, the electrical properties changed dramatically, and at low enough temperatures, the resistance dropped to 0. The reaction from the physics community was electric. Within weeks, labs around the world were scrambling to reproduce the result and push the temperature higher. And they did, fast. By replacing the lanthanum with other rare earth elements, samarium, cerium, neodymium, groups in China, particularly Zhongxian Zhao's team at the Chinese Academy of Sciences, drove the critical temperature up to about 55 Kelvin by the spring of 2008. 55 Kelvin in an iron-based material. That's still well below liquid nitrogen temperature, so you can't cool these with cheap nitrogen the way you can with YBCO. but it was high enough to make people sit up and pay very close attention. And what made the iron pnictides so exciting wasn't just the temperatures. It was the fact that they represented an entirely new class of superconductor, with a different crystal structure, different chemistry, and potentially a different pairing mechanism than the cuprates. The cuprates had their copper-oxygen planes. The iron pnictides had iron-arsenic planes. The cuprates were antiferromagnetic insulators that became superconducting when you doped them. The iron pnictides were antiferromagnetic metals, or at least semimetals, that became superconducting when you suppressed the magnetism through doping or pressure. There were deep parallels, but also deep differences, and that combination is exactly what physicists love, because it gives you a chance to figure out what's essential and what's incidental. Think about it this way. If you only have one example of something, it's really hard to know which features matter. It's like if you'd only ever seen one bird in your life, say, a robin, and you were trying to figure out what makes something a bird. You might think redness is essential, or a certain size, or a particular song. But once you see a penguin and an ostrich and a hummingbird, you start to understand which features are truly bird-like and which are just robin-specific. The iron pnictides were the penguin of superconductivity. They looked completely different from the cuprates, but they shared some deep structural similarities: the layered architecture, the proximity to magnetism, the emergence of superconductivity when magnetic order was suppressed. And that proximity to magnetism turned out to be a crucial clue. In the cuprates, remember, the copper-oxygen planes have strong antiferromagnetic correlations. The electron spins want to alternate, up, down, in a checkerboard pattern. When you dope the material and disrupt that magnetic order, superconductivity emerges. In the iron pnictides, something similar happens, but the magnetic structure is different. The iron atoms form a square lattice, and in the undoped parent compounds, they develop what's called a stripe antiferromagnetic order. The spins align in one direction along stripes and alternate between stripes. When you suppress that stripe order by doping or by applying pressure, superconductivity appears. So in both cases, you have magnetism and superconductivity living right next door to each other, almost competing for the same electrons. And in both cases, the superconducting pairing seems to be mediated not by phonons, not by lattice vibrations, the way BCS theory describes, but by magnetic fluctuations. Spin fluctuations, the ghost of the magnetism that was suppressed. Now, I want to be careful here because this is still an area of active research and debate. The pairing symmetry in the iron pnictides appears to be what's called S+-, which is different from the D-wave symmetry of the cuprates. In S+- pairing, the superconducting gap, the energy gap that protects the Cooper pairs, has the same sign on some parts of the Fermi surface and the opposite sign on other parts. The Fermi surface, by the way, is just the surface in momentum space that separates the occupied electron states from the unoccupied ones. In the iron pnictides, the Fermi surface has multiple sheets, hole pockets at the center and electron pockets at the corners of the Brillouin zone, and the gap changes sign between these pockets. That sign change is the fingerprint of a magnetically mediated pairing mechanism, because the antiferromagnetic fluctuations connect those different parts of the Fermi surface. If that felt a little dense, don't worry. The key idea is simpler than the details. In conventional superconductors, the glue that holds Cooper pairs together is vibrations of the crystal lattice. In these unconventional superconductors, both the cuprates and the iron pnictides, the glue seems to be magnetic. The very magnetism that you might expect to destroy superconductivity is, in a beautifully ironic twist, what makes it possible. It's as if the material's tendency toward magnetic order gets frustrated, redirected, and that frustrated magnetic energy becomes the binding force for Cooper pairs. And here's what's really lovely about having two different families of unconventional superconductors to compare. The cuprates are ceramics, brittle, hard to work with, oxygen sensitive. The iron pnictides, while not exactly easy to handle, are metals. They're more isotropic, meaning their properties don't vary as dramatically between different crystal directions. Their grain boundaries are less destructive to current flow. In some ways, they're more forgiving materials to engineer with. The critical magnetic fields in some iron-based superconductors are extraordinarily high, higher than in many cuprates, which makes them potentially very useful for high-field magnet applications. And because they're metals rather than ceramics, they can be made into wires more readily using conventional metallurgical techniques without the elaborate powder-in-tube or coated conductor gymnastics that the cuprates require. So the Iron Age of superconductivity, as some people started calling it, opened up both new physics and new engineering possibilities. Groups around the world, in Japan, China, the United States, Germany, everywhere, dove into the iron pnictides and quickly discovered a whole zoo of related compounds. There were the so-called 1111 compounds, like the original Leophias. There were 122 compounds, like barium iron arsenic, which had a simpler crystal structure and were easier to grow as large single crystals, making them favorites for fundamental studies. There were 111 compounds, 11 compounds, iron selenide, Fe, which is structurally the simplest of them all, just layers of iron and selenium with nothing in between, and which superconducts at only about 8 Kelvin in bulk, but, remarkably, shows signs of superconductivity at much higher temperatures when grown as a single-layer film on certain substrates. Some reports have claimed evidence for superconductivity in monolayer Fe on strontium titanate at temperatures above 65 Kelvin, possibly even higher. The interface itself seems to enhance the superconductivity, which is a whole fascinating puzzle of its own. But let's step back from the technical details for a moment and think about what was happening to the field as a whole during this period. Because the discovery of the iron-based superconductors in 2008 created a second wave of excitement that echoed, in some ways, the frenzy of 1986 and 1987. Not quite as explosive. The cuprate revolution had been a once-in-a-generation event, but the iron pnictides brought thousands of researchers back into superconductivity who had drifted away and attracted new ones who had never worked in the field before. Conference sessions were packed. Pre-print servers were flooded. There was a palpable sense that the landscape of superconductivity was much richer and stranger than anyone had imagined. And that sense was reinforced by other discoveries happening in parallel, because the cuprates and the iron pnictides weren't the only unconventional superconductors people were finding. There were heavy fermion superconductors, compounds containing rare earth or actinide elements where the effective mass of the electrons is hundreds of times larger than normal, and where superconductivity coexists with exotic magnetic states. There were organic superconductors. Yes, superconductors made from carbon-based molecules, first discovered in the early 1980s by Denis Jerome and Klaus Bechgaard, with critical temperatures that are low, but whose very existence is remarkable. There were superconductors based on Buckminster fullerene, the soccer ball-shaped carbon molecule C60, doped with alkali metals, reaching critical temperatures around 33 Kelvin. There was magnesium diboride, MgB2, discovered to superconduct at 39 Kelvin in 2001 by Jun Akimitsu in Japan, which stunned everyone because it's a simple binary compound and it turned out to be a conventional phonon-mediated superconductor, just one where the electron-phonon coupling is unusually strong. 39 Kelvin from good old BCS physics. Nobody had thought that was possible. Each of these discoveries added another piece to the puzzle, another data point in the quest to understand what makes a material superconduct and how high the critical temperature can go. And each one challenged the community's assumptions in a different way. The heavy Fermion superconductors showed that superconductivity could emerge from the most strongly correlated electron systems imaginable. The organic superconductors showed that you didn't need a metal or a ceramic. You could build superconductors from molecules. Magnesium diboride showed that conventional BCS theory still had surprises up its sleeve. And the iron pnictides showed that magnetism and superconductivity weren't enemies at all. They were dance partners. So by the early 2010s, the field of superconductivity had this incredible richness to it. Multiple families of materials, multiple pairing mechanisms, critical temperatures ranging from millikelvins to over 100 Kelvin, and a growing sense that the theoretical framework needed to explain all of this was going to be far more subtle and powerful than anything that existed. BCS theory was still the foundation. Cooper pairing was still the universal feature. But the glue holding the pairs together, the symmetry of the pairing, the role of the lattice and the electrons in the spins, all of that varied from family to family in ways that were only beginning to be understood. And then around 2015, a completely different approach to high-temperature superconductivity started producing results that nobody expected. Instead of searching for new materials at ambient pressure and hoping for high critical temperatures, a group of researchers decided to take ordinary materials and squeeze them incredibly hard, under pressures that exist naturally only deep inside planets. And what they found when they did that was nothing short of astonishing. They found superconductivity at temperatures that would have seemed like pure fantasy just a few years earlier. Temperatures approaching and even exceeding room temperature. Now, to understand why this was such a big deal, you need to appreciate what pressure does to a material at the atomic level. Think about it this way. Every solid you've ever touched, the table, the floor, the phone in your hand, is mostly empty space. Atoms are tiny nuclei surrounded by electron clouds, and those clouds keep atoms at certain distances from each other. The bonds between atoms have preferred lengths, preferred angles. That's what gives a material its structure, its personality. But when you squeeze a material hard enough, you're forcing those atoms closer together than they want to be. You're changing the distances between nuclei, warping the electron clouds, altering the way electrons hop from atom to atom. And when you change the electronic structure, you change everything. The way the material conducts electricity, whether it's magnetic, whether it's an insulator or a metal, and crucially, whether it can superconduct. This idea wasn't new. Theorists had been predicting for decades that hydrogen, the simplest and lightest element, might become a superconductor at very high temperatures if you could squeeze it hard enough. The reasoning goes back to a prediction by Neil Ashcroft at Cornell, who published a remarkable paper in 1968, suggesting that metallic hydrogen compressed so intensely that it stops being a gas or even a molecular solid and becomes a metal, could be a high-temperature superconductor. The logic was elegant. In BCS theory, the critical temperature depends on a few key things: the strength of the electron-phonon coupling, the density of electronic states near the Fermi level, and the frequency of the phonons, those vibrations of the crystal lattice. Hydrogen is the lightest element, which means its atoms vibrate at the highest frequencies. Higher phonon frequencies, in the BCS framework, translate directly into higher potential critical temperatures. And if you could metallize hydrogen, you'd have plenty of free electrons to form Cooper pairs. So, on paper, metallic hydrogen was the dream superconductor. The problem was that metallizing hydrogen requires absolutely monstrous pressures. We're talking somewhere around 400 to 500 gigapascals. That's 4 to 5 million times atmospheric pressure. For reference, the pressure at the center of the Earth is about 360 gigapascals. So you need pressures that exceed what exists at the core of our own planet. Generating those pressures in a laboratory is extraordinarily difficult, and even when you can do it, you can only do it to a tiny, tiny sample. We're talking about a speck of material smaller than a grain of sand, squeezed between two diamond tips in a device called a diamond anvil cell. A diamond anvil cell is a beautiful piece of engineering, actually. Picture two gem-quality diamonds, each ground to a precise shape with a flat face, called a culet, that might be only 50 or 100 microns across. You place your sample between those two flat faces, surrounded by a gasket that keeps everything contained, and then you press the diamonds together. Because the contact area is so small, even a modest force translates into an astronomical pressure at the sample. Diamonds are used because they're the hardest known material, and they're transparent, which means you can shine light through them and actually do spectroscopy on your sample while it's being crushed. It's a remarkably clever setup, but it limits you to samples that are almost microscopically small, which makes measurements incredibly challenging. So for decades, the dream of metallic hydrogen superconductivity remained just that, a dream. People tried to metallize hydrogen and made incremental progress, but the pressures required were right at the edge of what diamond anvil cells could achieve, and confirming superconductivity in such tiny samples under such extreme conditions was fiendishly hard. But here's where the story takes a turn. In 2004, Ashcroft published another influential paper, this time suggesting a workaround. Instead of pure hydrogen, what about hydrogen-rich compounds, materials where hydrogen atoms are packed densely into a crystal structure alongside heavier atoms? The heavier atoms would provide a kind of chemical scaffolding. They'd help stabilize a metallic structure at lower pressures than pure hydrogen would require. But you'd still get the benefit of those light, fast-vibrating hydrogen atoms driving strong electron-phonon coupling. It was a brilliant conceptual move. You're essentially using chemistry to pre-compress the hydrogen, to put it into a dense metallic-like arrangement without needing quite as much brute mechanical force. This idea lit a fire under the high-pressure community. Theorists began using powerful computational methods, density functional theory and its extensions, to predict which hydrogen-rich compounds might be stable under pressure and which might superconduct. And the predictions were tantalizing. Compounds of hydrogen with elements like sulfur, calcium, lanthanum, yttrium. The calculations suggested that some of these could have critical temperatures well above 100 Kelvin, maybe even above 200 Kelvin, at pressures that were extreme but achievable with diamond anvil cells. The first big experimental breakthrough came in 2015 from a group led by Michael Arametz at the Max Planck Institute for Chemistry in Mainz, Germany. Arametz and his team took hydrogen sulfide, yes, the gas that smells like rotten eggs, loaded it into a diamond anvil cell, squeezed it to about 150 gigapascals, and found superconductivity at around 203 Kelvin. That's minus 70 degrees Celsius. Now, That's still cold by everyday standards, but in the world of superconductivity, it was a bombshell. 203 Kelvin shattered the previous record of about 164 Kelvin held by a mercury-based cuprid under pressure. And here's the thing that made it especially satisfying for the theorists. The superconductivity in this compressed hydrogen sulfide appeared to be conventional. Good old BCS, phonon-mediated pairing. The same basic mechanism that Bardeen, Cooper, and Schrieffer had described back in 1957, just cranked up to 11 by the extreme conditions. Under pressure, the hydrogen sulfide transformed into a compound with the formula H3S, 3 hydrogen atoms for every sulfur atom, arranged in a crystal structure where the hydrogen atoms formed a dense, interconnected cage. Those hydrogen atoms vibrated at enormous frequencies, coupling strongly to the conduction electrons, and the result was a critical temperature that would have been unthinkable for a conventional superconductor just a few years earlier. It was as if BCS theory, which everyone had assumed had a ceiling somewhere around 40 Kelvin for conventional materials, suddenly revealed that it had no ceiling at all. You just had to find the right material under the right conditions. Arametz's result was initially met with some skepticism, which is healthy in science. Measuring superconductivity in a diamond anvil cell is notoriously tricky. Your sample is a speck. Your electrical leads are hair-thin wires that have to survive crushing pressures, and there are all sorts of artifacts that can mimic a superconducting transition. But the evidence accumulated, resistance dropping to 0, the isotope effect matching BCS predictions when deuterium was substituted for hydrogen, and eventually magnetic measurements consistent with the Meissner effect. The community came around, and then the race was on. If hydrogen sulfide could superconduct at 203 Kelvin under pressure, what about other hydrogen-rich compounds? The computational predictions pointed toward lanthanum hydride as an especially promising candidate, and in 2019, 2 groups, Arametz's team in Mainz and a group led by Russell Hemley and colleagues, then associated with George Washington University, both reported superconductivity in lanthanum hydride at around 250 Kelvin under pressures of roughly 170 to 200 gigapascals. 250 Kelvin is minus 23 degrees Celsius. That's a temperature you might experience on a cold winter day in Minnesota or Siberia. The idea that a material could superconduct at a temperature that humans actually encounter in daily life, even if it required enormous pressure to get there, was staggering. The compound responsible was LaH10, lanthanum decahydride, and its structure was extraordinary. Under pressure, it forms a cage-like arrangement where each lanthanum atom sits at the center of a cage made of 32 hydrogen atoms. The hydrogen atoms form an almost perfectly symmetric clathrate structure, and the phonon frequencies in this hydrogen cage are so high, and the electron-phonon coupling so strong, that BCS theory predicts exactly the kind of critical temperatures that were observed. Once again, conventional superconductivity, just in a regime that nobody had previously accessed. Now, you might be thinking, this is incredible, but what's the catch? And the catch is obvious. You need 170 gigapascals of pressure. That's not something you can build into a power line or an MRI machine. These experiments are scientific triumphs, proof of concept demonstrations that show what's physically possible, but they're a long, long way from practical applications. The samples are microscopic, the pressures are planetary, and the moment you release the pressure, the superconductivity vanishes. So in one sense, these discoveries are the most exciting thing to happen in superconductivity in decades. In another sense, they're deeply impractical. But here's why they matter beyond the headlines. They tell us something fundamental about the physics. They confirm that there is no hard theoretical ceiling on critical temperature for phonon-mediated superconductivity. The old Migdal-Eliashberg framework, the more sophisticated version of BCS theory that handles strong electron-phonon coupling, works beautifully for these materials. The predictions from computational theory matched the experiments remarkably well, which means we actually understand the mechanism. That's a powerful thing. It means that in principle, if you could find a material that naturally has the right combination of light atoms, strong bonding, high phonon frequencies, and metallic behavior, without needing extreme pressure, you might be able to achieve very high critical temperatures at ambient conditions. That's the Holy Grail. And the high-pressure experiments serve as a kind of roadmap pointing toward the structural and chemical features that enable high-temperature conventional superconductivity. The computational side of this story deserves a moment of appreciation, actually. The ability to predict, from first principles, that a specific compound at a specific pressure will have a specific crystal structure and a specific critical temperature, and then to go into the lab and confirm it. That's one of the great success stories of modern condensed matter physics. Groups like those of Yanming Ma in China and Artem Oganov, originally from Russia, developed powerful crystal structure prediction algorithms that could search through vast numbers of possible arrangements of atoms and identify the most stable ones at any given pressure. These computational tools became essential partners to the experimentalists, guiding them toward the most promising compounds and pressures to explore. It's a beautiful example of theory and experiment working hand in hand. And the search didn't stop with sulfur and lanthanum hydrides. Theorists predicted that yttrium hydride, calcium hydride, and various ternary compounds, hydrides containing two different heavy elements plus hydrogen, might push critical temperatures even higher. In 2020, a team involving Ranga Dias at the University of Rochester reported superconductivity in a carbonaceous sulfur hydride at about 288 Kelvin, roughly 15 degrees Celsius, which is genuinely room temperature, at around 267 gigapascals. If confirmed, this would be the first room temperature superconductor ever observed. The paper was published in Nature and made international headlines. But this is where the story gets complicated and, honestly, a little painful. Because the Dias result became one of the most controversial episodes in modern physics. Other groups had difficulty reproducing the findings. Questions were raised about the data analysis, about the way background signals had been subtracted from the raw measurements. An investigation by Nature led to the retraction of the paper in 2022, after the editors concluded that the data processing had not been handled with sufficient rigor and transparency. Dias disputed the retraction and maintained that the result was real, but the damage to credibility was severe. A subsequent paper by Dias's group, claiming superconductivity in lutetium hydride at near ambient conditions, was also retracted amid similar concerns about data integrity. Independent replication attempts by other labs did not confirm the extraordinary claims. This episode is worth sitting with for a moment because it illustrates something important about how science works, especially at the frontier. The pressure to achieve a landmark result, literally the most sought-after goal in condensed matter physics, is immense. And when you're working with samples you can barely see, under pressures that push your equipment to its absolute limits, where the signals you're looking for are tiny and the potential for artifacts is large, the standards of evidence have to be extraordinarily high. The community's response, demanding independent replication, scrutinizing the data analysis, ultimately retracting papers that didn't meet the standard, That's science functioning as it should, even though the process is messy and contentious and sometimes unkind to the people involved. So where does that leave the high-pressure superconductivity story as of the mid-2020s? The results for H3S at 203 Kelvin and LaH10 at around 250 Kelvin are broadly accepted by the community. They've been reproduced by multiple groups. The theoretical framework explains them convincingly, and they represent genuine milestones. The room temperature claims remain unverified and controversial. The dream of room temperature superconductivity is tantalizingly close enough that you can almost touch it, but it hasn't been conclusively achieved yet, and certainly not at ambient pressure. And that qualifier, at ambient pressure, is the one that really matters for practical applications. Because even if you could confirm a room temperature superconductor at 200 gigapascals, you'd still need to find a way to bring that behavior down to pressures that are actually usable. Some theorists are optimistic that metastable phases, crystal structures that form under high pressure but can potentially be preserved when the pressure is partially released, like a diamond that formed deep in the earth but persists at the surface, might offer a path forward. Others are exploring whether clever chemistry, doping, or nanostructuring could stabilize high-temperature superconducting phases at lower pressures. It's an active, exciting, and deeply uncertain frontier. Meanwhile, the quest for understanding superconductivity has been quietly revolutionized by another set of tools and materials that most people outside the field have never heard of. Starting around 2018, physicists discovered that if you take 2 sheets of graphene, single atom-thick layers of carbon arranged in a honeycomb lattice, and stack them with a tiny twist between them, something magical happens at a very specific angle. And what they found at that angle was something nobody had predicted. At about 1.1 degrees of twist, just a hair more than 1 degree, barely anything at all. The electrons in this twisted bilayer graphene system suddenly slowed down. They stopped behaving like the zippy, free-moving carriers you'd expect in graphene, and instead became what physicists call flat-band electrons, particles whose energy barely changes no matter how fast they're moving through the lattice. And when electrons slow down like that, when their kinetic energy becomes negligible, the interactions between them start to dominate. It's like a crowded room where everyone was rushing past each other too quickly to notice anyone else, and then suddenly the whole crowd slows to a crawl, and everyone starts bumping into each other, forming clusters, picking fights, making friends. The physics of interaction takes over. This was the work of Pablo Jarillo Herrero and his team at MIT, and when they published their results in early 2018, the condensed matter community went a little wild, because what they found at that magic angle wasn't just one exotic state, it was several. Depending on how many electrons you put into the system, which you can control by applying a voltage through a nearby gate electrode, the twisted bilayer graphene could become an insulator, which was surprising enough on its own, or it could become a superconductor. A superconductor, from carbon, from 2 sheets of atoms, each one just a single atom thick, twisted by barely more than a degree. The critical temperature was low, around 1 to 3 Kelvin, so you still needed serious cooling. But that almost didn't matter, because the implications were enormous. Here's why. For decades, the central frustration of high-temperature superconductivity research had been that the systems were complicated. Cuprates are layered ceramics with multiple elements, oxygen content that has to be precisely controlled, crystal structures that are difficult to grow, and even harder to study cleanly. Iron pnictides have their own complexities. High-pressure hydrides exist only inside diamond anvil cells at millions of atmospheres. All of these systems are, in different ways, messy. They work, and they're fascinating, but they make it very hard to isolate what's actually causing the superconductivity, to strip away the noise and see the essential mechanism. Twisted bilayer graphene changed that equation. Here was a system made of just one element, carbon, in the simplest possible geometry, two flat sheets, with a single tuning knob, the twist angle. You could control the electron density continuously with a gate voltage. You could make the same device switch between insulating and superconducting just by turning a dial. And the whole thing was two-dimensional, which made it amenable to a huge range of experimental probes. It was, in a sense, the cleanest possible laboratory for studying how superconductivity emerges from strong electron-electron interactions. Now, you might be thinking, 1 Kelvin is pretty cold. Why should anyone care about a superconductor that only works at 1 Kelvin when we already have materials that superconduct at 250? And that's a fair question. But the value of magic angle twisted bilayer graphene, which physicists quickly started calling MATBG, because nobody wants to say that full name more than twice, the value of MATBG isn't in its critical temperature. It's in what it teaches us. It's a model system, a playground where theorists and experimentalists can work together to understand the deep connection between electron correlations, insulating behavior, and superconductivity. Because one of the biggest open questions in all of condensed matter physics is whether there's a universal mechanism that connects the Mott insulating state, where electrons are stuck in place because they repel each other too strongly to move, with unconventional superconductivity. The cuprates hint at this connection. The iron-based superconductors hint at it from a different angle. And now MATBG shows the same pattern in a system so simple and tunable that you can watch the transition happen in real time. Think about what that means for a second. It's like having a wind tunnel for superconductivity. You can't fly a real airplane in a wind tunnel, but you can learn everything you need to know about how air flows over a wing. MATBG is the wind tunnel. The cuprates and hydrides are the real airplanes. And the story didn't stop with bilayer graphene. Within a couple of years, researchers started exploring other twisted systems. Twisted trilayer graphene, twisted double bilayer graphene, even twisted layers of transition metal dichalcogenides like tungsten diselenide. Each of these systems has its own set of magic angles, its own flat bands, its own zoo of correlated electron states. The field exploded into what people started calling twistronics, a name coined by Alan MacDonald, a theorist at the University of Texas at Austin, who, along with Rafi Bistritzer, had actually predicted the flat band phenomenon back in 2011, 7 years before it was experimentally confirmed. MacDonald and Bistritzer had published a theoretical paper showing that at certain twist angles, the band structure of twisted bilayer graphene would flatten dramatically, and most people had ignored it. When Dario Herrero's experiments confirmed the prediction almost exactly, MacDonald went from being a theorist with an interesting but overlooked paper to being one of the most celebrated physicists in the field. It's one of those stories that reminds you how important it is to take theoretical predictions seriously, even when they seem unlikely. So, by the early 2020s, the landscape of superconductivity research had become extraordinarily rich. You had the cuprates, still not fully understood after nearly 4 decades, but still holding the record for the highest temperature superconductor at ambient pressure, a mercury-based cuprate at about 133 Kelvin, or around 164 Kelvin under modest pressure. You had the iron-based superconductors, offering a different window into unconventional pairing. You had the high-pressure hydrides pushing toward room temperature but trapped inside diamond anvil cells. You had MATBG and the twistronics revolution offering unprecedented tunability and theoretical clarity. And you had a handful of other exotic systems, heavy fermion superconductors, organic superconductors, topological superconductors, each contributing pieces to the puzzle. But let's step back from the frontier for a moment and talk about something that often gets lost in all this excitement about higher temperatures and exotic mechanisms. Because while researchers have been chasing the dream of room temperature superconductivity, the superconductors we already have, the ones that work at liquid helium or liquid nitrogen temperatures, have been quietly transforming the world in ways most people never think about. Let's start with the one you're most likely to encounter, even if you never realize it. MRI machines. Magnetic resonance imaging, the technology that lets doctors see inside your body without surgery and without X-rays, depends entirely on superconducting magnets. The heart of every MRI scanner is a coil of superconducting wire, usually niobium titanium, a type II superconductor that works at liquid helium temperatures, wound into a solenoid and cooled to about 4 Kelvin. That coil carries a persistent current that generates a powerful, extraordinarily uniform magnetic field, typically 1.5 to 3 Tesla, which is tens of thousands of times stronger than Earth's magnetic field. And because the wire is superconducting, the current flows without any resistance, which means the magnet doesn't need a continuous power supply. You energize it once, and the current just keeps flowing. Some MRI magnets have been running on the same persistent current for years. Think about that. There's a magnet in your local hospital that was charged up years ago, and the current is still circulating, undiminished, because the resistance is exactly zero. Not almost zero. Not negligibly small. Zero. That's superconductivity doing real work in the real world, right now, today. There are roughly 50,000 MRI machines operating worldwide, and every single one of them is a superconducting device. And then there's particle physics. The Large Hadron Collider at CERN, the machine that discovered the Higgs boson in 2012, uses over 1,600 superconducting magnets to bend and focus beams of protons traveling at 99.9999% of the speed of light. Those magnets are made of niobium titanium wire, cooled to 1.9 Kelvin, colder than outer space, by superfluid helium. They generate fields of about 8 Tesla, and they have to be extraordinarily precise, because even a tiny deviation in the magnetic field would send the proton beam off course. The LHC is, in a very real sense, the largest superconducting system ever built. 27 kilometers of tunnel, packed with superconducting magnets, all cooled to less than 2 degrees above absolute zero. It's an engineering achievement that would have been utterly impossible without superconductivity. And there's fusion energy. The ITER project, currently under construction in southern France, is designed to demonstrate that nuclear fusion, the process that powers the sun, can be harnessed for energy production on Earth. ITER's tokamak, the donut-shaped chamber where hydrogen plasma will be heated to 150 million degrees, is surrounded by enormous superconducting magnets made of niobium tin and niobium titanium. These magnets generate fields of up to 13 Tesla to confine the plasma, and they have to operate continuously and reliably for long periods. Without superconducting magnets, the power required to maintain those fields with conventional copper electromagnets would be so enormous that the reactor would consume more energy than it produced, defeating the entire purpose. There's also a newer generation of fusion startups, companies like Commonwealth Fusion Systems, a spin-off from MIT, that are using high-temperature superconductors specifically a material called REBCO, rare earth barium copper oxide, which is a descendant of those cuprate superconductors discovered in the late 1980s. REBCO tape can operate at higher temperatures and, crucially, can generate much stronger magnetic fields than the older niobium-based wires. Commonwealth Fusion Systems has built a magnet using REBCO that achieved 20 Tesla, which is the strongest field ever produced by a high-temperature superconducting magnet of its kind. Stronger magnets mean you can build a smaller tokamak, which means lower costs, faster construction, and potentially a more practical path to commercial fusion power. So the cuprate superconductors that Bednorz and Muller discovered in 1986, the ones that set off the Woodstock of physics and all that frenzy, those materials are now, nearly 4 decades later, being engineered into magnets that might help solve the energy crisis. That's a long arc from a laboratory curiosity to a technology that could change civilization. And I haven't even mentioned superconducting quantum computers, which use tiny superconducting circuits cooled to about 15 millikelvin, 15 thousandths of a degree above absolute zero, to create qubits, the fundamental units of quantum information. Companies like Google, IBM, and others are building quantum processors based on superconducting circuits called transmons, which exploit the fact that current in a superconducting loop is quantized. It can only take on certain discrete values to encode and manipulate quantum information. Google's Sycamore processor, which in 2019 claimed to have achieved quantum supremacy by performing a calculation that would take a classical supercomputer thousands of years, was built from superconducting qubits. The entire field of superconducting quantum computing exists because of the macroscopic quantum coherence that superconductivity provides. The fact that billions of electrons move in lockstep, behaving as a single quantum entity, which makes it possible to build quantum devices that are large enough to fabricate and control, but still fundamentally quantum mechanical. So when you hear about the quest for room temperature superconductivity, it's worth remembering that the superconductors we already have are not just laboratory curiosities. They're inside hospitals, particle accelerators, fusion reactors, and quantum computers. They're enabling science and technology that would be flatly impossible without them. The reason room temperature superconductivity matters so much isn't that superconductors aren't useful now. It's that they could be so much more useful if you didn't need all that cryogenic infrastructure. Imagine superconducting power lines that could transmit electricity across continents with zero loss. Imagine maglev trains that didn't need expensive cooling systems. Imagine quantum computers that operated at room temperature. The technology would become cheaper, simpler, and accessible to everyone, not just the institutions that can afford liquid helium and dilution refrigerators. And that brings us to one of the most surprising and controversial episodes in recent superconductivity history, one that played out not in a prestigious physics lab, but on the internet in the summer of 2023, when a team of researchers in South Korea posted a preprint claiming they had discovered a room temperature, ambient pressure superconductor, a material they called LK99. And what happened next was unlike anything the field of superconductivity had ever experienced, because this wasn't a story that unfolded in the usual way. Through peer review, careful replication, and quiet consensus building over months or years, this one exploded across social media in real time, with millions of people around the world watching, debating, and refreshing their browsers to see if the laws of physics had just been rewritten. Here's what happened. On July 22, 2023, a group led by Sukbai Lee and Ji-hoon Kim at a small company in South Korea called the Quantum Energy Research Center posted 2 papers to RSEV the preprint server where physicists share work before peer review. The papers claimed that a material they called LK99, named after the initials of Lee and a colleague, Tae-Young Kim, and the year 1999 when they said the initial discovery was made, was a superconductor at room temperature and ambient pressure. Not at 200 gigapascals inside a diamond anvil cell. Not at liquid nitrogen temperatures. Just room temperature. Normal pressure. A material you could hold in your hand. The material itself was surprisingly simple. LK99 was described as a modified lead apatite. Basically, you take a mineral called lead phosphate apatite, which has a specific crystal structure, and you substitute some of the lead atoms with copper. The recipe they published was almost comically straightforward by the standards of materials science. You mix lead oxide, lead sulfate, and copper phosphide, heat them up in a furnace, and out comes this dark, somewhat crumbly material that, they claimed, exhibited zero electrical resistance and the Meissner effect at temperatures well above 300 Kelvin. Room temperature. Even above room temperature. Now, you might think the physics community would have been cautious, and many professional physicists were, actually, but the broader internet was not cautious at all. Within days, LK99 became a global phenomenon. The hashtag was trending on every platform. People were making memes. Stock markets in South Korea moved. There were breathless YouTube videos and Twitter threads and Reddit communities dedicated to tracking every development in real time. And the reason it caught fire so completely was partly the simplicity of the claimed recipe. This wasn't some exotic material requiring a billion-dollar lab. People started saying, some seriously, some jokingly, that you could make this in your garage. A few groups actually tried. But here's the thing. The evidence presented in those original papers was, to put it gently, not convincing to most experts. The resistance measurements were noisy and incomplete. The magnetic data was ambiguous. And the most dramatic piece of evidence, a short video showing a small, dark pellet of LK99 partially levitating above a magnet, tilted at an angle, was actually one of the biggest red flags. Because if you remember what we talked about earlier with the Meissner effect, a true superconductor expels magnetic field lines from its interior completely. A superconducting sample placed on a magnet would levitate stably, fully repelling the field. What the video showed was a sample that seemed to be half floating, half resting, tilted, and touching the magnet on one side. That behavior is actually more consistent with something called diamagnetism, a weak repulsion that many ordinary materials exhibit, rather than true superconductivity. Diamagnetic materials can do a partial levitation trick, especially if they're light enough and the magnet is strong enough. Bismuth does this, for example, and nobody calls bismuth a superconductor. So the professionals were skeptical from the start, but the public excitement was enormous. And then something genuinely remarkable happened. The scientific process played out at an unprecedented speed. Within days, not weeks or months, laboratories around the world started trying to replicate the results. Groups in China, India, the United States, Germany, and elsewhere synthesized LK99 or closely related materials and tested them. And the results came in fast. One by one, replication attempts failed to find superconductivity. Some groups did observe interesting things: unusual resistance drops, partial diamagnetic responses, but nothing that met the actual criteria for superconductivity. No zero resistance, no true Meissner effect. By mid-August, barely 3 weeks after the original papers appeared, a fairly clear picture had emerged. A team at the Max Planck Institute in Stuttgart, led by Pascal Poupal, synthesized high-quality samples and found no superconductivity whatsoever. A group at Peking University reached similar conclusions, and critically, several groups identified what was likely causing the misleading signals in the original data. It turned out that the synthesis process for LK99 tends to produce small amounts of copper sulfide, specifically Cu2S, as an impurity. And copper sulfide undergoes a structural phase transition at around 104 degrees Celsius, about 377 Kelvin, which causes a sharp drop in resistivity. If you're measuring your sample's resistance and there's a filament of copper sulfide running through it, you'd see what looks like a dramatic resistance decrease at a specific temperature, and if you weren't careful, you might mistake that for a superconducting transition. As for the partial levitation in the video, the consensus explanation was ferromagnetic impurities combined with the material's diamagnetic response, not superconductivity, just regular physics doing regular things that happen to look dramatic in a short clip. And so LK99 faded, not with a dramatic debunking or a scandal, exactly, but with the quiet, methodical machinery of science doing what it's supposed to do, testing a claim, finding it unsupported, and moving on. The original researchers maintained their claims for a while, but without reproducible evidence, the scientific community reached a broad consensus that LK99 was not a superconductor. Now, you might think this whole episode was just a waste of time, a flash of false hope that distracted everyone for a few weeks. But I'd argue it was actually kind of wonderful in a few ways. First, the speed of replication was extraordinary. The fact that dozens of labs around the world could synthesize a material, test it, and publish their results within days. That's the scientific method operating at a pace that would have been unthinkable even 20 years ago. Archive, social media, and the sheer number of groups with the right equipment meant that a claim could be stress-tested globally in real time. That's powerful. Second, LK99 showed just how much public appetite there is for a breakthrough in superconductivity. Millions of people who had never thought about Cooper pairs or Meissner effects were suddenly fascinated by the idea that a material could carry electricity without resistance. The excitement was real, and it reflected a genuine, widespread intuition that room temperature superconductivity would be transformative. People understood, even without technical backgrounds, that this would matter. And third, LK99 was a useful reminder of why the scientific community has the norms it does: peer review, careful measurement, independent replication. These things can feel slow and bureaucratic, but they exist precisely to catch errors, whether honest mistakes or something worse. The Rangadius retractions we talked about earlier, the LK99 episode, these are the system working, not the system failing. It just doesn't always work as quickly or as cleanly as we'd like. So where does that leave us? As of now, and I should say that now in a field this active can become outdated quickly, there is no confirmed room temperature, ambient pressure superconductor. The highest temperature superconductors that are broadly accepted by the community are still the high-pressure hydrides, like lanthanum decahydride at around 250 Kelvin. But those require crushing pressures that make them impractical for any real application. The highest temperature superconductors you can actually use at normal pressure are still the cup rates, YBCO and its relatives, operating at liquid nitrogen temperatures or somewhat above. And the workhorses of applied superconductivity remain niobium titanium and niobium tin for low-temperature applications, and Rebisio tapes for the newer high-field magnets. But the search continues, and it continues with more tools and more understanding than ever before. computational materials science has become enormously powerful. Researchers can now use density functional theory and machine learning to screen thousands of candidate materials, predicting their electronic structures and estimating whether they might superconduct before ever stepping into a lab. The Materials Genome Initiative, launched in the United States in 2011, and similar efforts worldwide have created vast databases of material properties that can be mined for patterns. The discovery of superconductivity in twisted bilayer graphene opened up an entirely new paradigm. The idea that you can engineer electronic properties through geometric arrangement rather than chemical composition, and the hydride work, despite its controversies, has genuinely expanded our understanding of what's possible at high pressures and pointed toward new chemical families worth exploring. There's also a deeper theoretical question that remains open, one that connects back to everything we've been talking about. We still don't have a complete, universally accepted theory of high-temperature superconductivity. BCS theory beautifully explains conventional superconductors, the ones where phonons glue electrons together into Cooper pairs. But the cuprates, the iron-based superconductors, the heavy fermion systems, the twisted graphene, these all seem to involve pairing mechanisms that go beyond simple phonon exchange. Magnetic fluctuations, spin resonances, orbital effects, electronic correlations, all of these have been proposed, and in different materials, different mechanisms may dominate. It's possible that there isn't one unified theory of high-temperature superconductivity, but rather a family of related phenomena that share the outcome: zero resistance, the Meissner effect, Cooper pairing, while differing in the microscopic details of how that pairing happens. And that's actually a beautiful situation, if you think about it. It means the landscape of superconductivity is richer and more varied than anyone imagined back when Onnes watched Mercury's resistance vanish in 1911. Every new family of superconductors has taught us something different about how electrons can conspire to flow without friction. Every surprise, the cuprates, the pnictides, the hydrides, the magic angle, has expanded the map of what's possible. There's a question that physicists sometimes ask each other, half seriously, half as a thought experiment. Is there a fundamental upper limit to the superconducting transition temperature? Is there some law of nature that prevents a material from superconducting at, say, 500 Kelvin or 1,000? And the honest answer is that nobody knows for certain. BCS theory, in its original form, seemed to suggest practical limits, but BCS theory doesn't apply to the high-temperature superconductors anyway. Some theoretical arguments suggest that very high transition temperatures should be possible in principle, especially if you can find materials where the coupling between electrons is extremely strong and the relevant energy scales are high. The hydrides seem to confirm this. Hydrogen is the lightest element, its phonon frequencies are the highest, and sure enough, hydrogen-rich compounds hold the temperature records. But getting from possible in principle to sitting on your desk at room temperature and normal pressure is an enormous leap, and it may require discovering entirely new physics or entirely new classes of materials. Or it may require a clever trick nobody has thought of yet. Some geometric arrangement, some interface effect, some way of stabilizing a metastable structure that happens to superconduct at 300 Kelvin. The history of this field is full of surprises that nobody predicted, so it would be foolish to say it can't happen. It would also be foolish to say it will happen next year. What we can say is that the journey itself, the century-plus arc from Leiden to Los Alamos, from liquid helium to diamond anvil cells, from mercury coils to twisted sheets of carbon 1 atom thick, has been one of the most extraordinary intellectual adventures in the history of science, and the people who've driven it forward have been a wonderfully varied cast of characters. Experimentalists with steady hands and an obsession with purity. Theorists who could see patterns in data that nobody else could see. Mavericks who ignored conventional wisdom and turned out to be right. And yes, a few who turned out to be wrong, or worse. But that's how science works. It's a human enterprise, with all the messiness and brilliance that implies. And there's one more thread I want to pull on before we start to wind down. One that brings together the practical and the profound in a way that I find really moving. It has to do with what superconductors have taught us, not just about materials or technology, but about the nature of quantum mechanics itself, about what it means for the quantum world to reach up and touch our everyday world. Because that's the thing about superconductors that doesn't get talked about enough. They're not just useful. They're not just fascinating puzzles for physicists. They are, in a very real sense, windows into the deepest layer of reality, places where quantum behavior, which usually hides at the scale of individual atoms, suddenly announces itself at a scale you can see with your naked eyes, hold in your hands, feel the weight of. Think about that for a second. Quantum mechanics governs everything, right? Every atom, every electron, every photon. But in everyday life, you never experience it directly. The quantum world is buried under layers of thermal noise, statistical averaging, the sheer overwhelming number of particles doing their own thing. A cup of coffee has something like 10 to the 25th molecules in it, all jostling around, and any quantum weirdness gets washed out in the chaos. The classical world, the world of solid objects and predictable trajectories and things staying where you put them, emerges from that averaging. It's not that quantum mechanics stops being true at large scales. It's that its effects become, for practical purposes, invisible, except in superconductors. In a superconductor, quantum mechanics doesn't hide. It steps right out onto the stage and takes a bow. And the reason is, those Cooper pairs we talked about way back near the beginning of our story, when we were exploring BCS theory. Remember, in a normal metal, electrons are fermions. They obey the Pauli exclusion principle, which means no two of them can be in the same quantum state at the same time. They're antisocial, if you like. They each need their own seat. But when electrons pair up into Cooper pairs, something remarkable happens. A pair of fermions behaves like a boson, and bosons are the opposite of antisocial. They love to pile into the same state. They're gregarious. They want to do exactly what every other boson is doing. So when a metal cools below its critical temperature and Cooper pairs start forming, all those pairs collapse into the same quantum ground state. They form what physicists call a macroscopic quantum state, or a condensate. And macroscopic is the key word there. We're not talking about one atom behaving quantum mechanically. We're talking about billions and billions of electron pairs spread across a chunk of material you could hold between your thumb and forefinger, all sharing a single quantum wave function. Let that sink in. A single wave function, describing the collective behavior of an astronomical number of particles, coherent across a piece of metal that might be centimeters or even meters long. It's as if you had a stadium full of people, and instead of each person moving independently, scratching their nose, checking their phone, shifting in their seat, every single person was executing the exact same motion at the exact same time, perfectly synchronized, without any conductor or signal telling them what to do. That's what a superconductor is. It's a quantum state you can pick up and put on a table. And this has consequences that go way beyond just zero resistance. The Meissner effect, for instance, the expulsion of magnetic fields that make superconductors levitate above magnets, isn't just a neat trick. It's a direct, visible manifestation of the rigidity of that macroscopic wave function. The condensate doesn't want to be disturbed. Magnetic fields would break the symmetry of the wave function, so the superconductor generates screening currents on its surface that exactly cancel the external field inside. It's the wave function protecting itself, and you can watch it happen. You can hold a magnet over a superconductor and see it float, and what you're actually watching is quantum mechanics enforcing its rules at a scale your eyes can resolve. That's extraordinary. There's almost nothing else in nature that lets you do that. Here's another one. Flux quantization. If you take a superconducting ring, just a loop of superconducting material, and you cool it down in a magnetic field and then try to change the field, you'll find that the magnetic flux threading through that ring can only take on certain discrete values. It's quantized, just like the energy levels of an electron in an atom. But this isn't a single atom. This is a ring that might be a centimeter across. Quantum discreteness, showing up at the scale of everyday objects. The reason is, again, the single-valuedness of the macroscopic wave function. As you go around the ring, the phase of the wave function has to come back to where it started. It has to be single-valued, and that constrains the magnetic flux to integer multiples of a tiny fundamental unit, the flux quantum, which is Planck's constant divided by twice the electron charge. About 2.07 times 10 to the minus 15 Weber, if you want the number. Tiny, but absolutely real and absolutely measurable. And then there's the Josephson effect, which might be the most beautiful example of all. Brian Josephson predicted this in 1962, when he was a 22-year-old graduate student at Cambridge. Just a kid, really, and some of the senior physicists didn't believe him at first. What Josephson showed, theoretically, was that if you take two superconductors and separate them by a very thin barrier, an insulating layer just a nanometer or two thick, Cooper pairs can tunnel through the barrier. Quantum tunneling, the same phenomenon that lets particles pass through walls, they classically shouldn't be able to cross. But here's the beautiful part. The tunneling current depends on the difference in phase between the two superconductors' wave functions. And if you apply a voltage across the junction, the phase difference evolves in time, and the current oscillates at a frequency that's exactly proportional to the voltage. Exactly. Not approximately. The relationship is F equals 2 eV over h. Frequency equals 2 times the electron charge times the voltage, divided by Planck's constant. And this is so precise that Josephson junctions are now used as the international voltage standard. When metrologists around the world need to define what a volt is, they use Josephson junctions, the quantum world, reaching up through a sandwich of superconducting material, defining the units we use to measure everything electrical. Josephson won the Nobel Prize for that in 1973, sharing it with Leo Esaki and Ivar Giaever, who had done pioneering work on tunneling in semiconductors and superconductors respectively. He was 33 years old at the time of the prize, and the work had been done when he was 22. Sometimes the young ones see things that the established experts miss, precisely because they haven't yet learned what's supposed to be impossible. And those Josephson junctions, as we touched on earlier in our journey, are exactly the elements that make superconducting qubits work. The transmon qubits that companies like IBM and Google use in their quantum processors. Each one is essentially a tiny superconducting circuit with a Josephson junction in it. The junction provides a nonlinear inductance, which is what creates the unequally spaced energy levels you need to isolate two quantum states and call them 0 and 1. Without that nonlinearity, you'd just have a harmonic oscillator, and all the energy levels would be equally spaced, and you couldn't address just the lowest two without accidentally exciting higher ones. The Josephson junction breaks that symmetry. It's a profoundly elegant solution, and it only works because of the macroscopic quantum coherence of the superconducting state. So when you hear about quantum computers getting bigger and more powerful, 50 qubits, 100 qubits, 1,000 qubits, what's actually happening at the physical level is that engineers are fabricating more and more of these tiny superconducting loops with Josephson junctions, cooling them to about 15 millikelvin in dilution refrigerators, and coaxing them to maintain quantum coherence long enough to perform calculations. 15 millikelvin. That's colder than outer space, colder than almost anything in the known universe. And the reason they need it that cold is the same reason Kamerlingh-Onnes needed liquid helium back in 1911. Thermal energy is the enemy of quantum order. At 15 millikelvin, the thermal fluctuations are so tiny that the delicate quantum states in those circuits can survive for microseconds, even milliseconds, which in the quantum computing world is an eternity, long enough to perform thousands of gate operations before the coherence decays. It's funny, isn't it? We started this whole story in a laboratory in Leiden in 1911 with a man who spent years figuring out how to make things cold enough to liquefy helium. And here we are, more than a century later, and the cutting edge of computing technology still depends on making things incredibly, absurdly cold. The tools are better. A modern dilution refrigerator is a marvel of engineering, with multiple stages of cooling, mixing chambers where helium-3 and helium-4 separate into phases and absorb heat as they mix. But the fundamental challenge is the same one Onnes faced. You want to see quantum behavior? Quiet the thermal noise, cool it down, let the quantum world speak. And maybe that's the most honest place to land as we start to let this story settle. Because the quest for room temperature superconductivity, the dream that's been driving researchers since Bednorz and Müller cracked open the cup-rate era in 1986, and arguably since Onnes himself, that quest is really a quest to hear the quantum world speak without having to make everything so impossibly cold. It's a quest to find materials where the pairing interaction is so strong, the condensate so robust, that it can survive the thermal chaos of room temperature, where quantum coherence doesn't need to be coddled and protected in a cryostat, but just exists naturally in a material you could hold in your hand on a warm afternoon. We don't know if that's possible. The honest answer, after everything we've talked about tonight, is that nobody knows. The theoretical arguments don't rule it out. The experimental record, the cup rates, the hydrides, the iron pnictides, the twisted bilayer graphene, shows that nature has many tricks for making electrons pair up, and we keep being surprised by new ones. But every material we've found so far either superconducts at temperatures that require serious cooling or at temperatures approaching room temperature, but only under pressures that would crush almost anything. The sweet spot, high temperature, low pressure, practical to manufacture, remains elusive. It's the Holy Grail, and like most Holy Grails, it may be found in a place nobody expected, or it may turn out to be a different shape than everyone imagined. But here's what I want you to carry with you as you drift off. Whether or not anyone ever finds a room temperature, ambient pressure superconductor, and I genuinely hope someone does, the story we've traced tonight is already one of the great stories of human curiosity. It starts with a man in the Netherlands who wanted to see how cold he could make things, and it leads to levitating trains, and MRI machines that save lives every day, and particle accelerators that reveal the building blocks of matter, and quantum computers that might someday solve problems we can't even properly formulate yet. It includes moments of breathtaking theoretical insight, like Bardeen, Cooper, and Schrieffer, working out how vibrations in a crystal lattice could make electrons fall in love with each other. It includes moments of pure experimental surprise, like Bednorz and Muller staring at a resistance curve that dropped to 0 at 35 Kelvin in a ceramic that nobody thought could superconduct. It includes the chaos and excitement of the Woodstock of physics, and the quiet, careful work of thousands of researchers who never made headlines but whose measurements and calculations built the foundation that everything else rests on. And it includes the failures too. The LK99 episode, with all its hype and heartbreak, the retracted papers, the careers damaged. Those are part of the story, because science isn't a smooth upward march. It's messy. It stumbles. It gets excited about things that turn out to be wrong. But it also has this remarkable self-correcting quality. Given enough time, given enough people checking each other's work, the truth tends to surface. The magnetic measurements get repeated. The crystal structures get analyzed. The impurities get identified. And the field moves on, a little wiser, a little more cautious, but still fundamentally driven by that same restless curiosity that made Ons spend years perfecting his cryogenic apparatus. So let that be the thought that accompanies you into sleep. Somewhere right now, in a laboratory you'll never visit, someone is cooling a new material down toward absolute zero, watching a resistance curve on a screen, waiting to see if it drops. Someone else is running a density functional theory calculation on a supercomputer, screening thousands of hypothetical compounds for signs of phonon-mediated pairing. Someone is growing a crystal, atom by atom, in a molecular beam epitaxy chamber, trying to build a structure that has never existed before. And someone, maybe a graduate student working late, maybe a little tired, maybe a little unsure if this is going to work, someone is about to see something unexpected. A dip in the resistance that shouldn't be there. A magnetic signal that doesn't fit the model. A data point that makes them lean forward in their chair and whisper, "Huh, that's strange." And that's how it always starts. That's how it started for Ons, and for Bednorz, and for Hosono, and for Harilo Herrero. A small anomaly, a quiet surprise, and then the long, painstaking work of figuring out what it means. The history of superconductivity is the history of people who paid attention to the strange thing, the unexpected thing, the thing that didn't quite fit, and who had the patience and the skill to follow it wherever it led. The electrons are out there, right now, in every piece of metal and ceramic and strange layered compound on Earth, doing their quantum dance. Most of the time, in most materials, that dance is chaotic, individual, washed out by thermal noise. But in the right material, at the right temperature, under the right conditions, they find each other. They pair up. They fall into step. And the resistance drops to zero, and the magnetic field gets pushed out, and the quantum world reaches up and touches ours. It's happened before, many times, in ways nobody predicted. And it will happen again. But that's a story for another night. For now, let the electrons dance, and let yourself rest. You've come a long way, from Leiden to Zurich, from a flask of liquid helium to a diamond anvil cell, from mercury to twisted graphene. The story will still be there in the morning, still unfolding, still full of surprises. And maybe, by then, someone somewhere will have found something new, something nobody expected, something wonderful. But for now, just breathe. Let the ideas settle like snow falling on a quiet field, and sleep.